Like the product rule, the quotient rule is more complicated than simply dividing the derivatives. This time, we'll immediately jump into the quotient rule theorem. So let's suppose that f and g are both differentiable at the point c, and that g of c is not 0. Then f divided by g is differentiable, and the formula for the derivative is given by this complicated monstrosity. There are similarities between this and the product rule, which should make this a little bit easier to remember. Primarily, in the numerator, we have the pairs f prime c g of c and f of c g prime c, though this time we're subtracting rather than adding them. Let's use this to differentiate the same function that we attacked in the product rule example. Only this time, instead of multiplying by 1 over x, we'll divide by x and use the quotient rule. Let's name the numerator function f of x, whose derivative we found in a previous video to be x plus 2 e to the x. We'll set g to be the denominator function x with derivative 1. Applying the quotient rule above, I'm going to take the time to write out the derivative formula just to emphasize it, to help you remember. Now let's plug in our functions above. And with a bit of factoring and some simplification, we get the same answer as we had before. And again, this just really highlights that there's no right way to compute a derivative. As long as what you've done is valid, you'll always get the right answer. The next example is a bit more abstract. If g is differentiable and non-zero at c, let's find the derivative of 1 over g. Let's take f to be the constant function 1, so that 1 over g is the same as f over g. Applying the quotient rule, and again, I'm going to write out the full formula for emphasis, we get this. Now f prime is 0 and f is 1, so there's a lot of simplification coming our way, leaving just negative g prime c over g of c squared. Even though this follows directly from the quotient rule, the above formula opens up a lot of derivatives for us. For example, if we differentiate e to the negative x by writing it as 1 over e to the x, then since the derivative of e to the x is itself, we get this. And canceling an e to the x term and rewriting this in terms of e to the negative x gives us our answer. Looking at the beginning and end of this equation, the derivative of e to the negative x is not quite e to the negative x, but rather picks up this extra negative sign. As a different example, let's suppose n is a positive number, and let's differentiate x to the negative n by writing it as 1 over x to the n. We know the derivative of x to the n by the power rule, giving us this. And if we simplify the exponents and rewrite it again in terms of x to the negative n, we'll get this. Thinking of negative n as its own number, this looks a lot like the power rule. And indeed, we can expand our statement of the power rule as follows. If n is any integer, which means that now we're allowed to use negative exponents as well, then the function x to the n is differentiable for all positive numbers, and the formula for its derivative is given by the usual power rule formula. Quotients thus complement our products and further expand our derivative toolbox.